Hi, I am Bryce Sandlund from the University of Waterloo. Our talk is on lazy search trees, and this is joint work with Sebastian from the University of Liverpool. So what is the problem? Problem description is to support the operations of a binary search tree. This includes rank, select, membership, predecessor, successor, minimum, maximum queries. And for updates, we'll have insert, delete with a pointer to the element, change key, again with a pointer to the element, and we'll do a split operation where we return two data structures of the same form with ranks less than equal to r and ranks greater than r, respectively, and a merge operation, which takes two data structures that have keys all less than or equal to, all the keys in T1 will be less than or equal to the keys in T2. And we're going to call this the sorted dictionary problem. And the reason we do so is that the standard dictionary problem, which only requires the membership, insert, and delete operations, you don't need to maintain order for that data structure. And in practice, the dictionary problem is solvable in constant time per operation using hashing. So what are the existing sorted dictionaries? Well, any balanced binary search tree fits our definition of a sorted dictionary. And I just have a few of them listed here, so the most important ones. They give you log n time per operation. We're just going to define log x to be minimum of 1 and log base 2x. And the splay tree in particular does support these theorems with slightly improved complexities for access times and amortized time. And I'll just describe them briefly here. First, there's a few of them. I only have a few listed. But yeah, so static optimality says roughly that you can access element I in time proportional to its frequency, or more efficiently if it's accessed more frequently. And the working set property says we can do it in log ti time, where ti is the number of items accessed since I was last accessed. And the dynamic finger property says we can do access of element I in the logarithm of the number of keys between j and I, where j is the last item accessed. The most important performance theorem of the splay tree is actually a conjecture, and that's that the splay tree is constant competitive to any other binary search tree on any sufficiently long access sequence. This is instance optimality here. And this conjecture has received a lot of attention. This was first proposed in the original splay tree paper. Then there's been some work on lower bounds. These are the Wilbur lower bounds, SciComp 89. We have the dynamic finger conjecture was proven in the 2000s. John Iacono gave the unified bounds. Then we have tangle trees, which are log n competitive in 2007 SciComp. And finally, a different proponent for dynamic optimality, which is this so-called greedy binary search tree in SOTA 2009. And there's even more publications based on this conjecture. Don't want to go through them all, but you can see they are very recent and in the most important theoretical computer science venues. So this motivates our work, and in particular, we ask a couple questions. And basically, the idea is, why are we we have all this work on optimal binary search trees, but in some sense, this is artificially restricting the number of data structures possible. We really care about trying to answer the operations, the requested operations, in as efficient time as possible. So we don't really need to restrict to a binary search tree. And if we don't restrict to a binary search tree, we can consider both insertion times and query complexities rather than just this access time, which is kind of a stand-in for both insertion and query in dynamic optimality literature. So motivation for this is the efficient party queue, the theory of efficient party queues. So we have Fibonacci heaps and derivative data structures that offer these improved runtimes if we restrict the operation set. So if we only ask for these extrema queries and don't worry about any rank other than minimum or maximum, then we can get these updates. Specifically, insert, we can do constant time instead of logarithmic. Change key as a decrease key could be constant time, again, instead of logarithmic. And we can even do this merge in constant time, and T1 and T2 can be arbitrary min or max heaps. So the question is, can we actually generalize efficient priority queues to support queries for any rank? If we could do so, then we would have a data structure, a sorted dictionary with superior insertion times to balanced binary search trees. So what is the intuition here? Well, binary search trees require sorting on an insert, but instead of doing that, we could just put the element somewhere and progressively sort as queries are answered. And this is kind of the idea in a couple areas that we'll discuss briefly. We'll first discuss multiple selection. So if you're not familiar with multiple selection problem, here's what it is. So we're given an unsorted array, and we want to select elements of particular ranks, R1 through RQ. So we have an unsorted array A here. And you see here, I have now partially sorted this array A just enough in order to answer, to be able to find the elements of rank 3, rank 7, and rank 13. And we can kind of discuss what the complexity of having to do such a what is the complexity of the multiple selection problem, and we define delta I to be a set of elements between consecutive ranks. We see here we actually need to find for each element, we need to find which of the delta I it falls into. And then we can define this B to be the sum of the cardinalities of delta I times the binary logarithm of n over cardinality of delta I. And if we do so, then the complexity of multiple selection is theta B plus n, so there's both a lower bound and matching upper bound. Okay, so we can now discuss all this related work. Now, there's two main categories, deferred data structures and multiple selection. So in deferred data structure literature, we just consider just the general idea of, okay, so this first paper is we want to answer Q queries on a stacked set of n unsorted elements. And it shows that we can do this in n log Q plus Q log n time. This was extended to make it Q prime queries, insertions, and deletions. And that's, again, a similar time complexity, except it's just a little more general. And then in multiple selection literature, there's a paper here in 2013 shows we can actually take these ranks and supply them online in any order and still get the same ending time complexity. Then we also have this, what I'll call kind of this semi-dynamic model. Right here we can do this online dynamic multiple selection in this time complexity, but we have to assume each insertion is preceded by a search for the inserted element. Okay, so now let's consider this literature, and I'm going to point out some issues that kind of make it less general than it could be. Okay, so the first issue is in deferred data structuring, we're not going to consider query rings. So we get these complexities, there's something like n log q, and this is not as good as what we're hoping for, because we're trying to generalize efficient priority queues. Now, a Fibonacci heap on n insertions and q queries can give you O of n plus q log n time, whereas this n log q is going to be a lot worse than that. So there's a lot of optimization that's left on the table by not considering query rings. And then in these semi-dynamic models, so to speak, we have this coupling of insert and query operations. So we're only considering these queries, insertions, and deletions together, and then this is going to give a bound that really is only meaningful if the number of insertions is very small, and we start off with a large set of initial elements. So the number of insertions is linear in the number of total elements. This is just going to be n log n, not very interesting. And the same thing happens here. In particular, this requirement of each insertion being preceded by a search for the inserted element is going to make this B become quite large based off of where the insertions are. And you can see it right here again. It's Q prime log n. Okay, so what is our model? Well, first I'll just briefly say that we're going to actually give our results at the end of this talk. This is a little bit unusual, but that way we can talk about them in the new model that we give so that they are meaningful. So we're going to take something similar to multiple selection literature. We'll partition elements into a set of gaps based on rank. And rank or key order, essentially. You just have all the elements in delta 1 are less than the elements in delta 2, less than or equal, and so on and so forth. And we can consider how this changes with dynamic operations. When we insert an element, we just need to put it in a place that respects the partition. So if we insert 8, it's going to fall in this gap delta 3. And now we can consider how a query should work, and this is going to be, it's kind of similar to multiple selection, but it's a little different, a bit of a generalization. And so if we have a query, it's going to fall in a particular gap, and we'll split the gap into two new gaps in a rank R that we will associate with the query operation. So we'll do an example here. If we're querying for the rank of 5 in our data set, well, we're going to associate the rank 9 with this operation, and that's actually the answer to the query. And we'll see here then we restructure this gap delta 2. I've now placed all of the elements of rank at most 9 left of the green line and more than 9 right of the green line, which coincides with elements smaller than or equal to 5 and larger than 5. And then we break up the gap into two new gaps, and there we are. Okay, so how do we choose this rank R? pretty straightforward. We want R to be basically where we need to recurse to answer these operations. Basically, exactly the rank we need to get to structure to in order to find the answer for the query. So for rank and membership, we'll just make R the rank of the queried element. And for select, predecessor, successor, minimum, and maximum, we'll make R the rank of the element returned. And for this update split, which is kind of also a query, R is just going to be the splitting rank in the argument. Okay, so what is the intuition? So multiple selection is going to fit pretty much directly into the framework. If I were to have a multiple selection problem with requesting rank 3 and rank 9, this is the set of gaps that results. Now we can also fit binary search trees into the framework. It's just every element gets its own gap. Now we maintain a sorted sequence. Interestingly, protoQs are going to actually correspond to a single gap, delta 1. And we can explain how, for example, an abstract minimum query is going to work. And we just perform a minimum query. Rank R is always going to be 1. And then I've swapped out these 1 and 6, which will then allow me to create this new gap, delta 1. And we've briefly made 2 gaps, with the first gap having a single element. We'll then extract the minimum, which must be in this gap, delta 1. And we return to the case of having a single gap. Okay, so we're going to end up using this B for the rest of the talk, so I'll keep it up there so we're reminded of what it is. And B characterizes the amount of information, really the amount of work we need to do in order to get to the current gap partition. So intuitively, if we're in the binary search tree case, we are sorting all the elements. This bound for multiple selection is n log n. You can see it here. Cardinality is going to be 1 for each delta I, so it's just log n for each gap. Similarly, a priority queue, the ProtoQ case with a single gap delta 1, we've now done no work. We haven't sorted the elements at all, and so B is actually 0. And then in a general case of just some kind of arbitrary gap, we're going to have B is going to be super constant, and it will be actually O of n log Q. So we see this n log Q term coming back organically from the related work. And the way this works is basically the most information is present if each gap has about the same size. That would be size of theta n over Q. Put that back into B over here. We get n over Q. Q goes to the numerator, and so it's just log Q. Okay, so our goal is going to be to achieve O B plus n time on an operation sequence resulting in a distribution of gaps delta I. And multiple selection is going to imply this is optimal. Multiple selection has O B plus n as a lower bound, and this fits within our model. Okay, so we can consider now how B is going to change on a per operation basis, and this is going to dictate our allotted time for each operation. So the change at B, so our first lemma is that the change at B due to insertion into the gap delta I is omega log n over the cardinality of delta I. And I'll just do this brief example here. It's pretty straightforward. I've given B exactly, and we see if I do this insert again, then I go from 3 log 2, 16 over 3 to 4 log base 2, 16 over 4. You can see this is about what we're going to get here. And I'll just note that these lower bounds we're going to give are over the worst case. It is possible to do faster than this if your operation sequence is particularly structured. Okay, so you get the rough idea of why this is about right. I won't go into the actual proof, but it's quite simple. And this is good because we can use this existing data structure, just a biased search tree, and we can weight each gap delta I with the weight, the number of elements in gap delta I. And a biased search tree it's just a binary search tree, except instead of each node getting unit weight, we allow arbitrary weighting of nodes, and the idea will be to make the heavyweight nodes be higher up in the tree, and that way we can access them quicker. So this is corresponding to my example here. And what we get in a biased search tree is that access to, well, the element I is going to take time log W over Wi, where W is the sum of all the weights, and Wi is the specific weight for our element I. So if we're accessing gap delta I, it's going to take log n over cardinality of delta I time, which is exactly what we wanted from our lemma 1. So we have a perfectly matching upper bound. Okay, now we can consider what needs to happen on our queries when we're doing these gap splits. And so here we have that the change in B due to splitting delta I into gaps of size Cx and x for C greater than equal to 1 is omega x log C. So I've defined it in this way just to try to make this bound as clean as possible. And we can just do a kind of a quick quick proof, so to speak, of why this is the case. Pretty straightforward. The number of ways to get find the x largest elements out of c plus 1x total elements is this c plus 1x choose x. We're considering comparisons as our only way of differentiating keys. And so there's only 2 outcomes in each comparison. Therefore, in the worst case, we can force our selection. It's going to have to take a log base 2 of the total number of elements. Do some basic asymptotics to get that this is omega x log c. And this is how we actually get the bound b for multiple selection. This is the lower bound for multiple selection. You could just do repeated single selections like this to get this total bound. So we could see that's how lemma 2 is x log c. All right, so I'll take a brief example here to look how this is going to work for priority queues. So in the priority queue case, there's only one gap, delta I. So insertion is just going to take log n over, well, this is actually n. So it's just log of 1. This is defined to be 1. This is constant time. Okay, and removal of the minimum, we now have x equals 1, and c is going to be theta n. And so O of x log c is just log n. And so we actually just get back exactly what priority queue literature has shown us to be possible. Our model gets this in a granular way, just looking at exactly what the cost of actually pulling these elements apart is. And okay, we can now go back to our lemma 2 and try to see how we can get an upper bound of O of x log c. And this is actually going to be our main technical challenge. I don't actually want to go into any of the technical details in this talk, however they are in the paper. And unfortunately, in our solution, we do add a log n additive term to insertion time in order to be able to support this splitting in O of x log c. So that makes our bounds not quite optimal, and I'll go through our performance theorems now. So yeah, as described, so we have this extra additive log n term, but we can say that over a sequence of n insertions and q unique queries, we get O of b plus, actually make this the min of n log n and n log q. And the reason I say unique queries is just because we need to have each query to create its own new gap in order for this bound b to be meaningful. Because otherwise, you can create a bunch of gaps and then get rid of them all. So we'll consider the per operation complexities in the next slide. And as described, this is omega b plus n is a lower bound, so we're within a log n factor, but it's an additive factor. Interesting thing about our data structure is our particular solution, if it's going to be implemented with arrays, we can just use the pointer machine if preferred, but we recommend the use of arrays in that if we do so, we can limit the amount of pointers required. Pointer-based data structures are notoriously slower than array-based data structures. When possible, an array is going to outperform a linked list. And similarly, a binary heap, which is based on an array, tends to be more performant in practice than the more complicated Fibonacci heap. And a lot of the reasoning behind this is because the Fibonacci heaps are pointer-based. So in general, just using less pointers and working mostly off of arrays allows you to get smaller constant factors, improved memory usage, and also better cache efficiency. And then finally, if we use this display tree as our biased search tree, then we can actually achieve those efficient access theorems for our data structure while also guaranteeing our efficient insertion time. So this is interesting because the display tree gives you efficient access times when the query sequence is non-uniform, and our theory gives us efficient insertion times when the query sequence is non-uniform. And if you combine them together, then you get a efficient data structure for non-uniform query access sequences. Okay, and the specific results, specific operation complexities, insert is about optimal with this additive log n. We can do query in O of x log c. This log n actually, this doesn't affect our overall performance in that we're still, it doesn't affect our overall performance because we see that in order to split a gap, on average, it's going to take at least log n time. And so this doesn't come out in the final bound in our theorem 1. But we can do this deletion in log n time. On the change key, so change key is something where if we're doing a priority queue, we can only do decrease key. We can't both decrease and increase key. And we can basically show some kind of a generalization to that for our model. The basic idea is we just have to decide whether we're going to support a decrease key or increase key in a particular gap delta I. We can also support decrease key on the lower half or increase key in the upper half. So I've just described it here. If this is my might be 22, I can change this rank to any of these ranks. And if we do have to change the gap that the key resides in, we're just going to have to do a delete and a reinsertion in log n time. Finally, construction we can do in linear time, so we can get rid of those log n factors if we have the set of elements initially. So split is going to be same time complexity as query. The actual split part is just a biased search tree split, which fits in log n. And similarly, the merge is also going to be a biased search tree, binary search tree merge, and it will also take log n time. Okay, and I can say that these insert, delete, change key, construction, merge will be worst case. However, our solution does require amortization to get these queries and splits in the desired time complexities. So it's probably not a big deal. Our query complexity actually can be as much as linear, and that's to say x log c can be linear if our gap delta I is of linear size, and x can be linear size, and so we might have to spend linear time on a query anyway. So this data structure is important when you need to get insertion complexity down, and you can afford not as efficient queries. However, the total time bound is going to be always within that of what a binary search tree gives. Okay, and I'll just get some brief applications here. And as described, yeah, we can replace binary search trees, and we can serve n insertions and q queries in O of n log q plus q log n time. And so this is interesting because this is similar to our related work in deferred data structures, except now I've completely decoupled the insertions and queries so that I have as many insertions as I want, and I don't need to consider starting with an initial set. And furthermore, I have it that yeah, my queries can now be completely general, any queries on a balanced binary search tree. As far as we know, I'm not aware of any query we can't support. You can see our paper for the exact requirements of the query. Okay, and further, I described that this data structure is good for non-uniform access sequences. I'll give an explicit example here. If we're trying to serve n insertions in q over k queries, but the q over k queries are these kind of range queries. We're looking for k consecutive keys. Well, then I can do this in time n log q over k plus q log n plus n log n. And so this is interesting because for most of our applications, we're going to be using the data structure only if the number of queries is particularly small, in which case the dominating term is n log q. And for here, this means that I essentially am getting these extra k keys. I'm kind of getting them for free because this n log q over k is likely to be the dominant term. And now each of the consecutive queries is just going to cost log n time, and it's not going to increase the relative amounts of work per insertion. So it's kind of interesting. Okay, we can also use our data structure as a priority queue or double-ended priority queue, log n time insert and decrease key. And now the interesting thing here is that we support a general operation set. We can now answer all the operations a binary search tree can answer. However, there's a trade-off here. If we introduce more gaps into the analysis, that's going to slow the insert and decrease key time complexities. And so yeah, this may or may not be interesting depending on the operation sequence. We are looking at trying to generalize this in such a way that no such trade-off is necessary. And we can use our data structure. Lazy searches can be used as a data structure for online dynamic multiple selection. And here, our dynamism is more efficient than previous solutions. And we do get this optimal time complexity within this additive n log n term. We can also use our data structure as an incremental quicksort. And here the interesting thing is internally, we actually, the way we make our splits, splitting the gap efficient, this is the main technical problem, is we're going to store elements in unsorted bags. And then we just gradually make the bags smaller and order the bags relative to each other. And when we make a bag smaller, we can choose to just pick a random pivot and create two new bags based on being either less or greater than that pivot. It actually turns out to be exactly what is done in quicksort. And so we can do things like this incremental quicksort work is to just start with an initial set of n elements and then return the q smallest elements in sorted order. We could do that in n plus q log n time. This is optimal. Or similarly, we could just sort any part of the array in optimal O b plus n time. And that's going to be it. Thank you so much.